Section: Introduction. In this section, we witnessed the rise of large language models, LLMs, and the fourth anniversary of the Vision Transformer, VIT, in 2024. VIT, born in 2020, transformed the computer vision field by using the transformer to process images as patches. It was inspired by encoder-only text transformers like BERT. VIT adopted the encoder-only design without using any causal mask for self-attention, influencing subsequent vision backbones and training methods. On the other hand, new LLMs with decoder-only architecture, such as LLaMA, OPT, and PaLM, emerged, showing great scalability in textual tasks. This led to a mismatch between encoder-only visual and decoder-only textual structures. We explored the idea of revitalizing decoder-only transformers in vision tasks. Through supervised learning, we found that LLaMA architecture could be modified to process input images effectively. We encountered an attention collapse issue during training, where adding a causal mask directly to the attention map caused the loss not to converge. To address this, we introduced a post-sequence class token technique, repositioning the class token to improve attention stability. We also investigated the benefits of causal self-attention in reducing complexity and enhancing attention map quality. Inspired by how humans observe things globally before focusing on details, we developed a soft mask approach to enhance network performance during training. We proposed a non-autoregressive decoder-only vision transformer called iLLaMA, incorporating causal self-attention. Our evaluations showed that iLLaMA performed well across various visual tasks compared to encoder-only models like VIT and Vision LLaMA. We also discussed the differences between encoder and decoder in transformers, focusing on the mask schemes in their self-attention mechanisms. Encoders use bidirectional self-attention, while decoders employ causal self-attention and cross-attention. We compared causal and bidirectional self-attention in terms of mask settings. Furthermore, we highlighted the distinction between autoregressive (AT) and non-autoregressive (NAT) models, with iLLaMA being entirely NAT-based for one-step inference, making it suitable for visual tasks. Our work aimed to align decoder design in LLMs with image models through supervised learning, showcasing scalability and improved performance on ImageNet 21K compared to existing models like Vision LLaMA. Section Summary. In this section, we explore the evolution of large language models, LLMs, and the Vision Transformer, VIT, since 2024, highlighting the adaptation of transformer architecture for computer vision tasks. We focus on the comparison between encoder-only and decoder-only transformers, proposing modifications like causal self-attention to align these architectures for improved performance in visual tasks. Our study introduces a non-autoregressive decoder-only vision transformer, iLLaMA, showcasing enhanced image processing capabilities and scalability compared to existing models like VIT and Vision LLaMA. Section: A Roadmap, Solving Attention Collapse and Optimization Improvement. In this section, we introduce the design roadmap of iLLaMA. We aim to adapt large language models, LLMs, to vision by using LLaMA and VIT as our references. Our trajectory consists of two dimensions: architecture and training techniques. First, we focus on block designs, including the feed-forward network, normalization layer, self-attention, and positional embedding. Next, we explore training techniques and introduce a soft mask strategy to aid optimization. We analyze efficiency and attention map rank as well. We begin with VIT T16 and VIT B16, gradually replacing their components with those from LLaMA. Experiments are conducted on ImageNet 1K, following a training recipe from the appendix. To address the differences between visual perception and text generation tasks, we maintain VID's non-autoregressive manner in our network. Each step change and its results are detailed in the appendix. The feed-forward network, FFN, structure in transformers differs between VIT and LLaMA, using multilayer perceptron, MLP, and SWI-GLUE, respectively. We substitute MLPs with SWI-GLUs, maintaining similar computational load. This substitution improves performance for both VIT-T16 and VIT-B16 models. Transformers require a normalization layer for stable training, such as layer normalization, lane, in VIT, and root mean square layer normalization, RMS norm, in LLaMA. We replace LNs with RMS norms in our network, observing increased accuracy for VIT-T16. The attention collapse issue arises from the casual self-attention component in transformers, where a lower triangular mask matrix is used. We introduce a post-sequence class token, PS/CLS, strategy to address this issue, improving network performance for both VIT-T16 and VIT-B16 models. By implementing the PS/CLS method, we eliminate the attention collapse issue and stabilize the training process, leading to improved network performance. This method proves effective in optimizing casual self-attention in a decoder-only image model. We will incorporate casual self-attention with the PS/CLS method in each block. Section Summary. In this section, we introduce the design roadmap of iLLaMA, aiming to adapt LLMs to vision by referencing LLaMA and VIT for language and vision practices. The trajectory focuses on architecture and training techniques, including block designs and a soft mask strategy for optimization improvement. By replacing components like feed-forward networks and normalization layers, and addressing attention collapse with a post-sequence class token strategy, we observe performance enhancements in VIT-T16 and VIT-B16 regimes, showcasing the effectiveness of these modifications in improving network optimization. Section: Positional Embedding. In this section, we utilized a standard VIT with learnable positional embedding, LPE, to maintain positional information by adding it directly to the patch embedding. We also explored the rotary positional embedding, ROPE, commonly used in LLMs, which operates within the attention of each block. Initially, we employed ROPE alone, enhancing the accuracy of VIT-T16 and VIT-B16 models to 72.6% and 81.2%, respectively. These results suggest that the concept of position in images and text is not fundamentally different. Since LPE only functions once before all transformer blocks, retaining it does not disrupt alignment with LLaMA within each block. Therefore, we reintroduced LPE, boosting the accuracy of the VIT-T16 model to 73.2%. This indicates that the two positional embeddings, LPE and ROPE, work together synergistically to enhance network performance. We decided to use both LPE and ROPE for positional embedding. After examining each block component, we finalized the architecture named iLLaMA. Moving on to training strategies, we adopted data augmentation techniques like mix-up and cut-mix from Deit's recipe to train our iLLaMA models. Unlike Deit's bidirectional self-attention, our model uses casual self-attention, impacting the connection between image tokens. The hyperparameters, mix-up and cut-mix, influence the input image content, which in turn affects the subsequent embedding. By experimenting with different combinations, we found that a mix-up of 0.1 and cut-mix of 0.1 improved the performance of iLLaMA T16 to 74.3%, while a mix-up of 0.95 and cut-mix of 1.0 led iLLaMA B16 to an accuracy of 81.3%. We also introduced a soft mask strategy to enhance optimization, inspired by how humans perceive objects. This technique gradually transitions from bidirectional to casual self-attentions during training epochs. The soft mask is a linear combination of bidirectional and casual masks controlled by a hyperparameter alpha. By adjusting the scheme, cutoff epochs, and learning rate warm-up, we observed performance improvements for both iLLaMA T16 and iLLaMA B16 models, achieving accuracies of 74.9% and 81.6%, respectively. Lowering the learning rate warm-up further improved iLLaMA T16 accuracy to 75.0%, but caused larger iLLaMA B16 training to fail to converge. Overall, using soft masks reduced the training loss in both models, addressing potential underfitting concerns. Section Summary. In this section, we explore the use of positional embeddings in ViT models, comparing learnable positional embeddings, LPE, and rotary positional embeddings, ROPE. By combining both LPE and ROPE, we introduce the LLaMA architecture, which enhances the accuracy of ViT models. Additionally, we propose a soft mask strategy to optimize model training, gradually transitioning from bidirectional to casual self-attentions, leading to improved performance in LLaMA T16 and LLaMA B16 models. Section: Analysis of Casual Self-Attention. In this section, we will analyze the benefits of using casual self-attention in LLaMA. We will focus on its efficiency in terms of computation and its ability to express visual representations using attention maps. When it comes to computational efficiency, we compared casual self-attention with a bidirectional baseline. We found that casual self-attention slightly reduces the number of flops, floating point operations, needed compared to the bidirectional baseline, especially as the sequence length increases. Moving on to attention map rank, we looked at how well casual attention can learn representations. By analyzing the singular values of attention maps from pre-trained models, we found that LLaMA has a more evenly distributed set of singular values compared to ViT. This suggests that LLaMA's attention map can be approximated by a higher rank matrix, potentially leading to more expressive visual representations. We have completed the design roadmap of LLaMA, highlighting its advantages in computational complexity and attention map rank due to its casual self-attention mechanism. However, to fully understand LLaMA's capabilities, further evaluations are needed, such as scalability for large models and datasets, model calibration, shape texture bias, and downstream task performance. Our experiments include a detailed evaluation of LLaMA, including ablation studies on data augmentation and soft mask strategies, comparisons with other baselines on ImageNet classification, and assessments of calibration, shape texture bias, quantization compatibility, and downstream task performance. In our ablation study, we found that the effectiveness of data augmentation strategies varies depending on the size of the LLaMA model. Additionally, the soft mask strategy proved to be robust to different hyperparameter settings, helping optimize LLaMA models and improve training and testing losses. Section Summary. In this section, we analyze the benefits of using casual self-attention in LLaMA, focusing on its computational efficiency and ability to enhance visual representation through attention map rank analysis. Casual self-attention reduces computational complexity compared to bidirectional baselines, with a more uniform distribution of singular values in its attention map, potentially leading to improved expressive capabilities in learning complex visual representations. The LLaMA model, featuring a decoder-only transformer with casual self-attention, demonstrates advantages in computational efficiency and attention map rank, with additional strategies like PS, CLS, and soft mask aiding in effective weight optimization during training. Section: Comparison with recent architectures on ImageNet 1K classification. In this section, we conducted experiments on the ImageNet 1K benchmark using various model sizes, i.e., LLaMA T, S, B, L, to assess their scalability. The ImageNet 1K dataset consists of 1,281,167 training images and 50,000 testing images across 1,000 classes. We trained LLaMA T-S-B on ImageNet 1K for 300 epochs with the Atom W optimizer and a batch size of 4,096. The LLaMA T-B models trained on ImageNet 1K resulted from the explorations discussed earlier. We slightly adjusted the soft mask schedule, cutoff epochs, and learning rate warm-up epochs for the LLaMA S model. For ImageNet 21K pre-training, we utilized the Winter 21 variant of ImageNet 21KP dataset, which includes 11,060,223 training images and 522,500 testing images from 10,450 classes. Only the training set was used. We pre-trained LLaMA BL on ImageNet 21K for 90 epochs with a constant soft mask schedule, setting cutoff epochs to 30 and learning rate warm-up epochs to 5. When fine-tuning on ImageNet 1K, we fine-tuned the LLaMA B model at a resolution of 384 by 384. Similarly, the LLaMA B-L model, pre-trained on ImageNet 21K, was fine-tuned at resolutions of 224 by 224 and 384 by 384. All fine-tuning was done for 30 epochs using the Atom W optimizer. We followed the DET method for interpolating positional embeddings to enable our LLaMA to handle inputs at higher resolutions. In terms of results, we compared LLaMA with other strong visual baselines on ImageNet 1K classification. Our observations are as follows. 1. LLaMA demonstrates a better performance parameter trade-off compared to other language model-inspired models like AIM and Vision LLaMA, likely due to its use of causal attention and soft mask training techniques. 2. LLaMA shows a superior accuracy throughput trade-off compared to hierarchical baselines such as Convenext V2N-T-B and SWIN-S-B, thanks to its isotropic design that benefits from a simple and efficient architecture, enhancing inference speed. 3. After extensive pre-training on the expanded ImageNet 21K dataset, the LLaMA B model achieves over 85.0% accuracy on ImageNet 1K with fewer than 100 million parameters, outperforming VIT-B's 84.0%. Scaling up to the larger LLaMA L model, the accuracy reaches 86.0%, surpassing VIT-L pre-trained on ImageNet 21K and AIM-7B pre-trained on the DFN2B Plus dataset, showcasing state-of-the-art performance for LLaMA-type architectures. We also examined the calibration properties and shape-texture bias of LLaMA for a more detailed evaluation, alongside Convenext and DET3 architectures. Model calibration, which assesses the model's precision and confidence across samples of varying difficulty, showed that LLaMA has lower calibration than DET3, indicating more reliable output confidence. In terms of shape-texture bias, LLaMA exhibited the largest shape ratio among the compared baselines, suggesting the potential of the LLM architecture for vision tasks. Section Summary. In this section, we conducted experiments on the ImageNet 1K benchmark with different model sizes to assess scalability. We trained LLaMA models on ImageNet 1K and ImageNet 21K datasets, achieving superior performance compared to other architectures due to its causal attention and soft mask training techniques. Additionally, we evaluated LLaMA's calibration properties and shape-texture bias, showing lower calibration error and a higher shape ratio, indicating its potential for vision tasks. Section. Compatibility with quantization. In this section, we explore the compatibility of LLaMA with quantization. We conduct quantization-aware training on LLaMA by adjusting the weights and activations of certain layers to 8 bits. The quantization process and outcomes can be found in the appendix and table, respectively. Different versions of low-bit LLaMA maintain accuracy effectively, with the 8-bit LLaMA T model even performing competitively with the full-precision DET-T model. Moving on to transferability on downstream tasks, we focus on CIFAR transfer learning. By fine-tuning VIT-T and LLaMA-T on CIFAR datasets, including an analysis of the soft mask on LLaMA, we observe that LLaMA's performance on CIFAR datasets is comparable to VIT. This indicates that LLaMA can be a reliable option for transfer learning, serving as a practical alternative to VIT. Moreover, the soft mask proves beneficial in the more complex CIFAR 100 dataset, showcasing its versatility. For ADE20K semantic segmentation, we fine-tune pre-trained LLaMA and VIT models on the ADE20K dataset using UperNet for semantic segmentation. Setting the learning rate and weight decay parameters, we compare the performance in a table. While LLaMA's performance is slightly lower than VID's, we attribute this to the impact of the masking mechanism in LLaMA's causal attention on tasks requiring high-resolution dense predictions. This suggests that there is room for further optimization, which we plan to investigate in future studies.